Let us start this lecture with a thought process by great poet and Nobel laureate Rabindranath Tagore, who says everything comes to us that belongs to us if we create the capacity to receive it. It is indeed a very complex and poetic statement, but if I can decipher for you, it will be like this, that we will have to develop our capacity such that we can fructify our desire, not just dreaming for it, rather working for it. So, let us recall what we learned in the last lecture. In the last lecture, we basically discussed about various types of propellant grain, and it is very important to have various types to meet the various requirements depending on the application. And if you look at, we basically looked at two types of grain, end burning grain and also side burning grain. And these two are generic in nature, because in end burning grain the propellant will be burning along the longitudinal axis, and in case of side burning grain it will be regressing along the radial direction. And then various kinds of combination permutation one can have. We have discussed about 2-dimensional propellant grain, 3-dimensional, and also various kinds. Let us start this lecture with summarizing these types of propellant grain, and we can classify the solid propellant grain into 4 categories. One is the production, and depending on the manufacturing techniques which is being used, right, and also how it is being done, one can also look at it. One is freestanding, that means how you pack the propellant in a combustion chamber, and also it can be casting, it can be extrusion method, right. And other one is case bonded. Case bonded, it can generally will be casting, and whereas the freestanding can be both cast method and the extrusion method. And this does affect the regression rate to some certain extent. And the another way of classifying the solid propellant grain is composition. Composition of a propellant can vary very different way. I have just mentioned 2 of them. One is double base propellant, rather it comes under heterogeneous combustion propellant. It can be single base, it can be triple base composite propellant, and there can be mixed of that is known as composite modified double base propellant. There is also another kind of propellant grain is known as nitramine propellant, and of course, you can add these explosive materials like RDX, HMX to double base and composite, and also together there are various kinds one can. And of course, in the last lecture we concentrated more on the geometry. One is the end burning grain and other is the side burning grain. And as I told earlier, the end burning grain will be having basically the regression of the propellant will be moving along the longitudinal direction. In the side burning, regression of the propellant will be moving along the radial direction. And side burning can be divided into 2 categories. One is 2-dimensional grain and other is 3-dimensional grain. If you look at several examples I have taken, let us look at some of them. One is which is being used very much is your star, and there can be also the double anchor, and there can be also the multi perforated, there can be also the dog bone, These are the thing what we have discussed. Of course, there are various other kinds as well. And another thing we discuss also wagon wheel and several others kind of thing. And among all these 2-dimensional propellant grain, generally the star is being used very much, because in this case one can really get all kinds of burning, because if you look at, we have also look at nature of burning, that is your regressive burning and neutral burning, and other is the progressive burning. So, all these 3 types of burning you can get in star, that depends on the number of vertices it is having. For example, in this star grain you can get 5 vertices, 1, 2, 3, 4, 5. And if I take this as a center, if you look at this one, then this is basically can be one side and then this angle, and this angle will be equal to pi by n. N is the number of vertices, n is the number of vertices. In this case, this is equal to 5, 1, 2, 3, 4, 5. That means the total side burning surface like this is a basically side burning surface will be 10, and keep in mind that this is your angle, this is basically theta by 2, and this will be angle will be theta between 2 side burning surfaces. And if this theta will be more, become higher, you will get progressive burning. That means, for larger values of theta, one can get progressive burning, and for smaller one values of theta, this is theta, this angle between 2 surface is will be getting basically regressive burning. And in between that you can get a neutral burning. That is why it is being used very much, and it is really designer love it to have the star burning, because one can get whatever they want to have, particularly the kind of burning they want to have. And 3D grain is quite complex and difficult to design and develop. However, it has been tried out. The 3 kinds what we have discussed is, one is cono seal, and then other is the pheno seal. Basically, this is a cone plus cylinder surface you are talking about, and other is the spherical. Already we have discussed about that, and then simplest one is a cone cylinder, and the spherical one is quite complex, and also it is having lot of limitation, but good, but advantage of the spherical 3D grain is that L by D ratio will be very small, and also the compact as compared to other 3D grains. So, let us look at a little bit about how does the burning surface in a solid propellant grain evolve, because that is very important to find out how much really the mass of propellant being burned for a particular time, and also how you will get the thrust law, and by knowing the chamber pressure. And for that we will have to use certain principles, basically laws, so that we can calculate. Generally, the propellant regresses layer by layer. Beside this, that or any point on the surface of the grain regresses normal to the tangent surface at that point. Let us consider a N burning grain propellant. And this is your, let us say, solid propellant, which is N burning grain. And when I am saying that it will be going by layer, basically this is the, if it is regressing this direction, that there will be layer by layer it will be regressing. That means, if I take a point here and then this surface, this is your propellant surface or surface of grain, I can say, of grain. So, if I take a point, this will be regressing in this direction perpendicular to this tangent plane, and this is your tangent plane. And this law is basically known as the pivot law. This is known as the pivot law, and this one has to look at it. Let us look at what really will happen when you are having a cast, convex cast toward the gas. So, this is cast means basically edge, and this is your edge, which is two surfaces are meeting. And this, as per the this pivot law is concerned, that if I take a point here, it is moving basically toward that. That means, this is your grain surface, this is one surface and this is also another surface, and it is moving towards the solid as it regresses, and then this also will be moving and this person also will be moving. So, that this point is retained and it will not be really changing. But if you look at other one, that is, it is the surface is here gas, this is your grain surface or the propellant surface. So, also this one, this is also this one. So, in this case it is concave towards the gas. So, therefore, this will be perpendicular, will be moving, but however, in this case this will be moving in this direction. So, it will be making a curved one arc, this is the arc will be making, and whose point center will be this edge or the cups. This is basically cups, you can say cusp and or the edge. So, therefore, this will be made it as a curve. So, this one has to keep in mind while calculating how the surfaces will be evolved when the regression of the propellant is taking place. So, let us look at that a cylindrical propellant grain, and in this case it is having a length L and this is a port diameter, this is port diameter, and in which it is really combustion is taking place, and this is your grain surface, and as it is going through. So, if you look at it is having a diameter d and this length is basically small d, and this when it regress it will be regressing this way. So, this is the surface which will be going, that means it will be regressing in this direction perpendicular to direction. So, keep in mind that this will be the wave is basically, that is the wave thickness. W we call is the wave thickness, that is the amount of propellant along the radial direction which can be getting consumed when the propellant surface regresses towards the periphery of in this propellant gas. And in this case, this wave thickness is very important, because that is the amount of propellant which will be burnt during certain time. And this wave thickness, in this case it will be basically d minus small d divided by 2. And keep in mind that if I want to find out how much time it will take for the burnt out, if the Tb is the burn out time, that means the grain surface or the burning surface will be reaching the metal surface. That means there will not be any propellant which will be really burnt out. So, that is the burnt out time. So, if I want to find out this basically what will be the burning surface area, or at time t is equal to 0, that A B 1 will be basically the perimeter of this S B into L, and this is S B is the perimeter, and this A B 1 will be basically pi d into L. At t is equal to T b, that is your burnt out time, I can say A b final will be pi, I can say almost thickness, neglecting the thickness of the combustion chamber, I can say d into L. So, if I want to find out what will be the wave thickness, I can do that very easily, that is W is equal to R dot T into 0 to T b. That means, I can get what will be the thickness by just, and whereas R dot is the regression rate. So, by this way I can calculate wave, I can also find out what is the amount of propellant we can have, provided we know the density of the propellant. And keep in mind that like we will be now taking an example to illustrate how we can calculate this. Let us consider this example. A designer has proposed to use propellant grain with a rectangular cross section of 0.2 meter and with an outer diameter of, this is basically meter square, of 1.5 meter and length of 2.5 meter, and the density of propellant is rho p 1295 kg per meter cube, and we will have to determine the sliver mass of the propellant grain and percentage sliver as compared to initial propellant at the end of its operation. When all the propellant when this propellant can really be consumed at the end of its operation, we can find out. So, if you look at these are the given, if I consider this is your A, if I consider this is your this A, and that is basically A is equal to 0.5 meter and length is 2.5 meter and diameter, this is your diameter, I can consider this is your diameter, and d is 1.5 meter and rho p is 1295 kg per meter cube. and we will have to find out basically sliver mass. That means, sliver mass is the one in which basically at the end of operation the propellant will remain intact, or in other words it cannot be really used further. So, let us look at what will be the sliver mass, and let us for that we will have to consider how this regression is taking place in this rectangular cross section propellant grain. So, if I take this as a center, I can and similarly I can draw this center, and if I take this here and then this is also this one, and we have seen that let us say this is O, and when there is a let us say delta amount of or a small amount is being regresses in this surface, and it can also go to this side, because in this case it is moving perpendicular to this plane. And keep in mind that in this case this is the A. So, this will be moving around like this, and similarly if I consider this and if I consider this, as this will be basically like that. If I consider the another, let us say I will use a color here, little bit different color, just so that you can find out what it would be. Let us say it moved again to another one, so again this became curve, became like this, it will be moving in this way. So, this will be moving in all the direction that way, in such that it will be reaching a point here. Let us say I will take this point somewhere here, and so this is reaching almost the that means this surface that means this surface which will be remaining at the end of this burning, because of fact that when it is regressing along this direction it will hit the metal surface. This is your metal surface of the combustors. So, you cannot really burn beyond this line, and this is known as sliver, or you can say total is the mass, sliver mass. And that means you cannot have operation when this regresses in a particular direction, particular corner points, and reach here, something like that, then you cannot have here. So, therefore, this sliver mass is very important. Generally in a good design, the 5% sliver mass is allowed, more than that it cannot be used. We will take this as a point here. Let us say this is your A, and this point if I consider this as a x, that means I will have to find out how much maximum wave thickness we are having. That means, this wave thickness can be from A to O. The wave thickness delta, wave thickness in this case will be delta, and that is your delta. or I can say this is also your delta kind of thing. This is your delta and this is also your delta. So, this delta will be basically equal to O x minus O a, and that will be equal to d minus O a. O a will be basically, if you consider O a is nothing but your I can get this A, and let us say this is your point B, right, A B, right, and this will be root over A square plus S square half. So, that will be O A, right. If I substitute these values, this is half into O x is basically your diameter is 1.5 minus root over, that is 0.5 square plus 0.5 square, because that is your A is delta is equal to basically 0.396 meter. And if you look at, we want to find out basically the sliver volume. The sliver volume can be is basically V s, and what it would be, if you look at the total the volume, that is your pi by 4 d square, and then this volume, this is the volume, what will be that, that is with respect to this, this is the portion, and what it would be, that will be equal to this area, that is your A square plus this is the area, right, and what will be this area, this will be basically A into delta, because this portion is delta, this portion is delta. So, plus 1, 2 like that, it is also this is 1 and this is also another 1, 2 and this is 1/3. That means, this is 1, 2, 3, 4 area plus 4 into A delta plus, and this area, this is the quadrant. If you look at, this is one quadrant, this is another quadrant. So, that I can write down 4 into pi by 4 delta square, because this is your delta radius, this is also delta radius. So, this is equal to that. So, this will be cancel it out, and if I substitute these values, I get pi by 4, d is 1.5 whole square minus 0.5 square plus 4 into 0.396 into A is there also A 0.5 plus pi 0.396 whole square, and you will get basically V s is equal to 0.581 meter cube. So, the sliver mass would be basically rho p into V s, that will give 1295 into 0.581, and that will be 752.2 kg, and the total propellant mass and into L, I think I have not added here L, and that will be 2.5. This length should be, because this is your volume into length. So, propellant mass would be rho p into V p, and that will be rho p into pi by 4 d square minus a square, because this is your the without any propellant, that is a square space, into L. And when you substitute this value 1295 into pi by 4, d is 1.5 whole square minus 0.5 whole square 2.5, you will get 4911.5 kg. So, percentage of mass, sliver mass would be ms divided by m p, this is your total mass, propellant mass, m p into 100. So, I will get 75.2 divided by 49115 into 100 is basically 15.3 percentage, which is quite higher as compared to the standard that is 5%. Hence, it is not really being used very much or for practical applications. So, with this we will stop over. In the next lecture, we will be discussing about basically about stability, and then later on we will be talking about the ignition system and also ignition energy that is required for the initiation of combustion in a solid propellant engine. Thank you very much.